And so our first talk will be by Dr. Bill Nazaroff, and the title of his talk is Transcending Complexity, Indoor Fine Particulate Matter Measurement, Exposure, and Control. Dr. Nazaroff?
Thank you, Dr. Matsui, and thank you to the committee and to the academies and to the US EPA for organization and for the invitation to share with you some thoughts. In the first session, I thought it addressed wonderfully this broad theme of transcending complexity, but in the realm of health effects related to indoor particulate matter. And for this talk, I want to focus more on the physical science aspects, the penetration of particles to indoor environments, the resulting exposures that occur, the control of indoor particulate matter viewed from a high perspective. And by transcending complexity, I mean acknowledging that this is a very challenging subject, but not letting that acknowledgement and the understanding of the complexity hinder our practical efforts to make progress. So to begin with, we've heard, but I'm an engineer and I like seeing some numbers, that fine particulate matter is a major contributor to ill health. And in fact, it's a surprisingly large contributor. So in the global burden of disease studies, we have numbers such as summarized in this table. The total number of people who died planet-wide in 2016 was about 55 million. Of that, it's estimated that 6 million, more than 10%, were associated with air pollution. And the large part of the air pollution problem was ambient particulate matter pollution, which, as Dr. Kippen pointed out this morning, is mostly an indoor or largely an indoor exposure issue in any case. Not mentioned very often in our meeting so far, but quite important, is that secondhand or environmental tobacco smoke is also a major contributor to ill health, on the order of 1 million deaths per year associated with that, primarily because of the fine particulate matter. And just to put these numbers in context, note that during the pandemic, as of a week or so ago, the global mortality during this first year associated with COVID-19 is on the same scale, about 3 million deaths. We've seen several times, so I don't need to dwell on this, so we spend most of our time indoors, 90% in all, and about 2/3 of our time is spent in our own residences. That means that most of the air we breathe is indoor air, and we've also heard several times, and I'll stress in this talk also, that indoor air is not the same as outdoor air. So you've heard this rule of thumb number, and I'll just provide you some additional supporting evidence that about half of the fine particulate matter that's outdoors penetrates and persists in the indoor environment. I worked in Singapore for several years, and there they suffer from wildfire smoke seasonally. It's actually from agricultural burning in the region. During one of these smoke episodes, we had several investigators carry personal portable PM monitors around with them. And the plot in the middle of this figure shows a trace of one day following an individual as that person spent time in a hotel overnight, then walked to work at a building called the Create Tower, then was indoors at the Create Tower, took a break at lunchtime, walked outside for a while, and then after another period of work, walked home and spent the evening in the hotel. And overall, both of these buildings provided about 50% reduction in the indoor concentration of particulate matter. Indoor sources in this case were not particularly important. It was mainly the penetration of particles from outdoors. But we also have to be concerned with indoor emission sources. These can include combustion activities or heating, but also can be mechanically generated through processes like coughing, sneezing, but even talking. Vacuuming is overall a cleaning activity, but temporarily resuspends particles and leads to elevated concentrations. And last week, Dr. Lindsay Marr spoke about the role of humidification as a contributor because of the impurities that are in the water that then gets created into a mist and emitted into indoor environments. So to summarize the state of complexity, I've highlighted here 4 dimensions. So let's just go through these 4 dimensions briefly. Of course, they're much richer than I can capture in a few minutes. From the standpoint of size, even considering the bulk of the PM 2.5 mass, we have about a factor of 250 range in particle diameter from 10 nanometers up to 2.5 micrometers. That range in diameter corresponds to 16 million times difference in mass between the largest and smallest particles. That same mass ratio applies if you consider mammals between the smallest mammal, the Etruscan shrew, and a very large mammal, a gray whale. In chemical complexity, the composition of fine particles includes elemental and organic carbon. The organic carbon has a vast range of specific chemical species that make it up. The crustal materials, inorganic salts, metals, and many other things contribute to the particulate matter that we find in our air. Temporally, we've heard, and I can affirm, that indoor concentrations can change quite rapidly on fast timescales. I would say a factor of 100 or more on a timescale of minutes is not unusual. And spatially, each building is its own distinct entity with its own indoor fine particulate matter level. And even within a building, concentrations may vary among rooms and within a room. And to just drill down a little further, we've heard a little bit of discussion. I'm presenting this from a little different perspective about respiratory tract deposition. So the figures here on the left consider the fraction of particles that are in the air that we inhale that get deposited in the three major regions of the respiratory tract: the head, the branching airways, the tracheobronchial region, and then the air exchange region, the pulmonary region. And you can see complex dynamic behavior across this span from 10 nanometers to 2.5 micrometers, with a quite markedly different likelihood of depositing if you're a large particle compared to a small particle in this range in the head, or a very small particle depositing in the tracheobronchial region versus an intermediate sized one. This, of course, has consequences for the physiologic response, because we have different clearance mechanisms and different disease sensitivities in the different regions. And so the simple statement here is that size matters. With respect to chemical complexity, here's a little drill down into some aspects, just considering the relationship between outdoor particles and indoor particles of outdoor origin. When those particles from outdoors come indoors, the temperature and humidity changes, which can affect the equilibrium partitioning for semi-volatile species, including water. There's surface uptake and emissions of gaseous species indoors, which can affect the condensation to and evaporation from particles. And we can have shifts in the liquid water and pH, which can then in turn alter the size and composition of particles. Temporally, concentrations vary markedly indoors, substantially in response to changing indoor conditions, especially indoor emission activities. Dr. Nina Vance showed this slide last week, and so I'll just highlight a few points from it. These are data collected showing particle mass concentrations with some size resolution as a function of time during an intensive experiment called the HomeChem study. And each of the frames represents a single day in that study with different kinds of conditions. Just stressing two of these, the sequential ventilation day down on the bottom, when there was no indoor activity other than to sequentially open and close the windows. And during this time, when the windows were open, the indoor particle levels went up. And then when the windows were closed, the indoor particle levels diminished. Conversely, at the top was a simulated Thanksgiving Day. And during this day, a Thanksgiving dinner was prepared, even though it was during June, and enjoyed by a large number of guests at the end of the day. And here, in addition to the strong temporal variability, I would note that the PM levels are hundreds of micrograms per cubic meter, well above the ambient air quality standard. In fact, that's summarized here, showing the time average PM concentrations, where there's a factor of 30 difference between the time average for Thanksgiving Day and the case of an unoccupied background condition indoors. Important aspect of the temporal variability is that if we rely on time averaged indoor concentration measurements without taking account of the correlation with occupancy, we can mischaracterize the indoor exposure. So this figure on the right illustrates that point by showing measurements made in a classroom. This is a university classroom, a relatively small one. It only held about 20 people. Over the course of one day, with particle sizes sorted into three categories. The smallest ones at the top, an intermediate size in the middle, and then the largest size for fine particulate matter at the bottom. And the red trace shows the indoor particle levels, whereas the black trace shows the simultaneously measured outdoor levels. You can see from the way that this figure moves from top to bottom that the very smallest particles, 0.3 to 0.5 micrometers, were not influenced by occupants, but the largest particles were strongly dominated by occupant presence and movement. And this is attributable to simply the shedding of particles from the occupant's envelope, from their clothing and from their skin, and also the resuspension from flooring. That shedding leads in turn to a complex spatial variability in indoor spaces. This is, to use Dr. Kippen's words, a little bit of a cheat because I'm showing PM10 data here, not PM2.5. But in this study, we had in a well-controlled chamber test where the background particle levels were quite low, we had some subjects placed in that space and we had them doing different activities in different experiments. So in frames A and B, they were seated and carrying out prescribed activities while we simultaneously made measurements of particle levels in their breathing zone, measured by the blue trace, and in the background room air, shown in pink here. And you can see that the levels in the immediate vicinity of their nose, the breathing zone levels, associated with release activities from their seated behaviors, normal occupant activities, were considerably higher than the room average levels. Conversely, when they walked around the room, the personal cloud, in this case, disappeared because the room floor was quite clean and the room air became relatively well mixed by their movement. This disagreement or spatial variability, if you will, between what's measured in breathing zone and the room background is referred to often as the pigpen effect or the personal cloud behavior. So how do we get past this complexity? I love this quote from Einstein: everything should be made as simple as possible, but not simpler. So let's talk about how we can make things simpler. For size complexity, let's use PM2.5 mass concentration or some suitable proxy as the best information we have if we want to aim for practicality now. But if we're concerned with ultrafine particles, and we should be, then we should probably be using number concentration for these smallest particles. This area is an ongoing challenge. We'll hear some more about aspects of that in the later talks in this session. For chemical complexity, I would suggest that the evidence to date does not implicate any compositional factors as a primary reason, and I emphasize here primary, reason for adverse health consequences of PM exposure. So I would say that from a practical orientation right now, if we aim to improve indoor environmental conditions, chemical complexity should be made secondary. It remains an active research issue, and as we learn more, maybe we should change that perspective. For temporal complexity, we have to be attentive to the fact that the conditions during occupancy is what we want to know. And so if we measure time average conditions, we have to be very careful to not misinterpret that what we're measuring on a time average basis is the same as what was there when people were present. And spatially, here, personal monitoring is better than stationary monitoring. And of course, indoor data are better than outdoor data. Let me pass through these next few slides a little bit quickly, that is, just skip them and instead use my last minutes to talk about the, if we have these guideposts, or if we're overall concerned about practicality, we want to make conditions better, how do we improve the gap between what we know and what we do? Which is a different gap than the gap between what we ought to know and what we do know. That latter gap is the subject of ongoing research. As we learn things there, we can move them to try to focus on this, translate them into an attempt to focus on this other space. So overall, for indoor air quality, quite apart from particles alone, or in addition to particles alone, there's this set of 4 ideas encapsulated into 12 words about how to try to make our indoor environmental conditions better. Minimize indoor emissions, keep it dry, ventilate well, and protect against outdoor pollution. I would use or suggest that these are guideposts. They need to be translated into specific actionable steps that we can take. And let's take a closer look now at how these might apply to indoor environments. First, minimizing indoor emissions. This is not new guidance. Back in the middle of the 19th century, Max von Pettenkofer wrote this in German, so I'm relying here on Google Translate. The translation's a little rough in points, but the idea is clear. A room containing a rotting dung heap will, despite all the ventilation, remain a disgusting dwelling place, a stove for bad air. That's the rough translation. Only when cleanliness can no longer be achieved by the rapid removal or careful closure of air-polluting substances does the field of ventilation begin. And specifically then, with respect to particles in indoor environments, what can we look to for source control? Tobacco smoke. I think it's no exaggeration to say that the biggest improvement in indoor environmental quality in my lifetime has been the massive change in our exposure to environmental tobacco smoke. It would be a good subject to investigate as a template for how to think about other indoor pollution sources, because it's not just technological, it's not just public messaging, it's not just regulation, it's a combination of many things that have led to that improvement. Cooking is another area where we've heard mention of, and we will hear more from some speakers next week. A range hood and its effective use is an important means of limiting cooking emissions. And then, of course, with respect to SARS and infectious disease transmission specifically, masking remains an area with some confusion, but one of the really important aspects of masking is for source control. That is, it reduces the degree to which infectious particles get released from the respiratory tract of people who are actively ill, and not only reduces the release of those particles, but attenuates the plume that can transmit them from the infectious person to a susceptible individual. Keeping it dry, I think Professor Lindsay Marr spoke well last week about the importance of mold and mold control, and so I don't need to dwell on that. One can find images like this on the web regularly. Mold is a major problem indoors. With ventilation, the story is complex, and many speakers have alluded to this complexity, so even if we try to make it simple, it's hard to make it simple. If we make the air change rate too low, then indoor pollution sources will dominate and the condition will not be so good. If we make the air change rate too high, we are going to use too much energy, and outdoor pollution sources like wildfire smoke will dominate. So we need to find the Goldilocks solution here, which is to ventilate well, but not excessively. Sufficiently, but not excessively. And specifically what that means is something that has to be elaborated, that this guideline of being someplace in the middle needs more elaboration. So I'm just going to leave the guideposts saying that it's a balancing act, and we want to find the right position in that balance. With my last few minutes, I would like to maybe present a preamble to what we will hear a lot more about next week, which is the use of filtration for particulate matter control. And I want to do this schematically, contrasting a few points, but also illustrating through this approach some means for how to think quantitatively about the intervention opportunities. So illustrated on the left is what I would call a closed path intervention. To protect the occupants of an indoor space from outdoor pollution, we put a filter in a mechanical supply airstream that would remove particles with some efficiency eta. And if we can avoid bypass and if we can avoid leakage in doing so, then we ought to strive for the most efficient device that we can achieve practically, so that that efficiency eta protects effectively the people indoors from outdoor particles. But that configuration doesn't protect people from indoor sources. An open path configuration would be a recirculating air filter with a fan unit applied indoors. And here the efficiency is denoted eta R. That's the fraction of particles passing through that are removed. But it is possible that this control measure will both reduce exposure to outdoor originating particles and reduce emission, the effect of emissions indoors on exposure. But it's an open path because both the outdoor particles and indoor particles can get to a susceptible individual without having passed through the filter. So we have performance metrics, the efficiency, which is a fractional removal, the clean air delivery rate, which combines the fractional removal with the flow rate through the device, and effectiveness. For effectiveness, we can talk about the extent to which the controlled condition is better than the uncontrolled condition. And so this expression represents the fractional reduction in exposure that would occur or concentration that would occur in the indoor environment by the addition of the device. If we're protecting against outdoor pollution, efficiency is the same as effectiveness if we have a closed path. And the key then for performance is to make that efficiency as close to 1 as we want to, or as we can. But with recirculating units, the efficiency and the effectiveness are not the same. And the goal then should be to achieve a high clean air delivery rate compared to the removal rates that occur by other processes. So specifically, here's a plot showing the air cleaner effectiveness, that is the fractional reduction in indoor concentration by the application of this device, plotted against normalized clean air delivery. And we have the key parameter is to make the clean air delivery rate high compared to the background removal rate. And an important point here is that we can effectively make indoor particle filtration better by using a higher flow rate with so much lower efficiency to get good overall effectiveness, because the goal is to make that product high, the clean air delivery rate. So to sum up in brief, I've got Einstein's quote here, reminding us to keep things simple. For ideas, guideposts, a reminder that indoor particulate matter is complex across many dimensions. That complexity is real. Sometimes it's important, but the complexity itself need not impede effective action. Thank you.
Thank you. That was terrific, Dr. Nazaroff. I have one question for you because we have just a couple minutes before the next talk, which is if you were to set the priority on a research agenda in this area, which is really focused on thinking about how to measure these exposures, what would that be?
Well, there are. I would take a step back maybe and think about where our intervention opportunities have the most potential. And I think it's through a combination of residential environment improvements and school environment improvements. In schools, it was a subject in the earlier presentation and we'll need to continue. The school situation is so divergent in the U.S. and actually so poorly managed in general with respect to ventilation that we have enormous challenges to address. But I think we heard some good points in the discussion in the first session this morning about the need for a guideline for schools that is expressed and attended to by authoritative bodies, and then regular monitoring and maintenance, which is a big upgrade from where we are today about system performance. Carbon dioxide has been mentioned, and I think that doesn't get us to the particulate matter question alone, but it does help with the issue of demonstrating the effectiveness of ventilation in crowded indoor environments like school classrooms. And I don't know if we're quite ready with the existing particulate matter monitoring techniques to use the low-cost sensors as a means to routinely monitor what's going on in schools, or whether we're better off by doing a more intensive monitoring on a selected basis. But that's an area where progress we should see some progress going forward pretty quickly.
Terrific, thank you. And I think that's a nice segue to our next presentation.